So you want to make sure and do those two things. And then where we are is that we have two items that are background items that help you to understand chapter 2, which has something to do with the pattern that how we can organize all the solutions of linear systems. And this is going to be sort of a consequence of the Gauss-Jordan method, which is also will start sort of next week. But in the background, we have some background information. We have to do some stuff about sets. So I just wanted to review some stuff about sets. And this is in the tutorial at the end of chapter 1. It's on page 70, following page 76. And there's just a few comments. So you're probably familiar with a set just is a collection of any items, and usually there's some set of items you're talking about. Sometimes it's called the universe of discourse, and we draw these diagrams where, like here, where you have a set A, each point in here is supposed to be an item. A set is a collection of items, of any kind of items. So if this dot represented X, then we'd say that X is in the set. We'd write that with the claim X is a member of A. And remember this A from our solution set. So A might be sort of a set of all possible sort of triples of numbers or something, and X would be one of the solutions of a linear system. Okay, and then if you draw this Y out here, then we'd say Y is not an element of the set A. And it's usual to use capital letters for sets. Okay, now what we need to deal with is not only operations that sets deal with, but we have to do with set equality, because we want to say, if we have two linear systems, we might want to say, well, the solution sets are the same or different. So if we have the solution set of one linear system, we say that's the same as the solution set of another linear system. For example, one of these might be the system you started with. The second one might be the solution set after you've done a row operation. Well, what does this mean? Well, conceptually, it means set equality means to set equality is two set. Well, we say S1 and S2 name the same set. Two set names name the same set. Well, the set is entirely determined by the items in it. Okay, so this is analogous to if I say 5 equals 2 plus 3. This is just saying the numerical value on the right is the same as the numerical value on the left. Okay, so this is sort of analogous. It's saying the items included on the left are the same as the items included on the right. Okay, well, the problem is this is sort of conceptually clear, but how do we use that to show, if we had two linear systems, that the solution sets were the same? Well, if I draw up these two sets in one of these Venn diagrams, there's several different possibilities. One is I could have like this, I'd have S1, S2, where there'd be some overlap. They wouldn't be the same, right? And this would be one possibility, but there's another possibility in which S1 is inside S2, in which this solution, this set has all the items in S1 are in S2, but not vice versa. And it could be the other way too. You could have S1 out here and S2. And so the question is, if the two sets are equal, well, we have this relation here says we have a symbol for this. The claim that all of S1 is inside S2, in symbols we write it like this. It's called a subset relation. And we'll come across subsets in other contexts, so it's useful to learn this notation and stuff. Over here, we'd say that S2 is a subset of S1. So S1 subset of S2 and S2 subset of S1. And you can think of subset here as being inside, because that's what this diagram shows, that S1 is inside S2. Now, what if they're equal? The diagonally, this would be S1 and this would be S2. Now, this equal sign means S1 is inside S2 or it could be equal to it. So if I said both, that S1 was inside S2 and S2 was inside S1, right? Because if this was the diagram here, then S1 would be inside S2 and S2 is inside S1. Well, this is what we mean in practical terms. If I wanted to show the two sets were the same, we'd show both of these, because here S1's inside or equal to S2. It could be this way or this way, but then this says, okay, but S2 has to be inside S1 also. So that this one cuts out this diagram, and this one cuts out this diagram where one of the sets is smaller. So this is equivalent to S1, S2. So there's a conceptual definition. They have the same two set designations that have the same elements, or really the same set. Okay? So if I want to show that two sets are the same, I need to show that S1 is a member of S2 and S2 is a member of S1. That's all I'm saying. Is these two expressions are logically equivalent. Is this, you guys have questions about this, or is this okay? Okay, this is what in this tutorial it says proving two sets are the same, right? Here's the subset relation. Oh, and how is the subset relation defined? Well, basically it means S1 is in S2 if all the elements in S1 are also in S2. So we can write that with this funny symbol for all elements. If E is in S1, then E is in S2. So this is the definition of what we mean by this. So here's a concept that's sort of vague because it's just in words. Like inside you have a diagram, but this is the logical form that's equivalent to this. So if you have to show that S1 is equal to S2, you could say, well, I'm first going to show this, then I'm going to show this. In order to show one, I would replace this concept with the specific definition, right? This is the, maybe you could put definition here. And then you do the same thing with S2 and S1 reversed for this one. And then since this is a conditional, you'd assume that E was in S1 and have to show that the other element was in S2. And so it's a very concrete thing, even though there's this little sort of paraphernalia technology to get around this. Okay, so, and here it goes back and talks about this some more stuff. And then it talks about unions and intersections and complements and operations with sets. And that's what I wanted. That's the sort of one concept here at the beginning with sets that I wanted to get across. There's some other ideas here, that we might do later, but now, if I go back to chapter 1, there was this, in here you'll find at the end of the chapter, you have this theorem that that it's the safety of Gauss's method. It's why it works. If a linear system is changed to another by one of the three row operations, then the two systems have the same set of solutions. Well, that's exactly what we would do here. Now, to show, there's a proof here, but it's long-winded, and the reason it's long-winded is because we have to choose names for all the things in a general n variable, n equation linear system, and it's just like all of these letters and numbers you're writing out, and you're writing out. See, there's the first one, and there's some arbitrary row I and some arbitrary OJ, and then you can think about exchanging the two. Well, so instead of like you can read this, but I can't really write it out because it's so many symbols. It would just, you just go to sleep. or I'd go to sleep. Anyway, so what I could do, though, is to see we could see what happens if we do it with a 3-element system. So you get the same idea. So if I take an arbitrary 3-element system, say A, X plus B, Y plus C, Z equals D, and then EX plus FY plus GZ equals H, and I'm going to leave off I because it's hard to see. IJX plus KY plus LZ equals M. Okay, well, I've just chosen letters instead of indices, and hopefully that's okay. Well, if I did, let's say that I wanted to say this has a certain solution set S1, right? And if this is the first equation, this is the second equation, and this is the third equation, then S1 equals all the triples of numbers, S1, S2, S3, that I could choose for X, Y, and Z. I could call this, say, S sub X, S sub Y, S sub Z, the numbers I would choose for X, Y, and Z. Well, S1 is all the SXs, SYs, SZs. I mean, let's just call this S for the solution, such that this is true. E1 of S and E2 of S and E3 of S. So you'd say that the solution set is this, is all the ones where this is true, right? Well, we could go there and ask, well, what does, if I go and look at the system that's gotten by doing a row operation, like let's say that I go and do a row operation. Let's say I do row 2 times K, where K is not equal to 0. Well, then I have a second system. And that second system has the same E1, right? But then I'm going to have KE2 for its second equation, which is going to be K times E. I'm going to multiply this whole thing by K times E times X plus K times F times Y plus K times G times Z equals K times H. And then E3 is the same as before. Same as above. So, but this is a second system. This is, so it's going to have an S2, which is all the triples SX, say, prime, SY prime, SZ prime, such that that E1 of S and E, and here KE2 of S and E3 of S is true. Well, the question is then, okay, if S is a solution, so we want to say, suppose some triple is a solution of S1. We want to show that these are the same solution sets, so we want to show that S1 is a subset of S2. So we want to show that if SX, SYZ is a member of S1, we suppose this, but we need to show it's a member of S2. Well, that means that if it's a member of S1, this is true, right? But that means that E1 of S is true, and E3 of S is true because they're true up here. So what we know is, we know that ES1, not ES, yes, ES1 plus F, that's FSX, FSY plus G, SZ, because I've replaced the X with SX, the Y with, we know this is true. Okay, well, but it's just arithmetic. I mean, we know these are all numbers. We know this is true. Oh, did I do that? It's just H. There's no K there. Oh, yes, there's just, well, I can just then say, well, if this is true, then K times E SX plus FSY plus GSZ is equal to, well, I can, since this combination here is the same as H, because we're supposing this, right? Because it's a member of S1, then it's true that K times H is true, because this is just, H is just a name for the same member as this. But that's what I wanted to show, because then we know that K times E2 of S is true. Therefore, if any triple is a member of S1, it's a member of S2. And you can see how, since K is not 0, I could run this backwards and say, okay, if I have a solution here of this equation, I can divide by K and show it's a solution of the first one, so I can show the two solution sets are the same. And that's what is done for all of the 3 row operations in here. If you walk through, see here I'm doing a row swap. So here I tell you why you can swap these with logic. And then here's the one we just did, but with more names. And then the last one is where I do K times 1 row plus another row. And you do the same, and you argue for the same operations. I think it's hard to even look at, right? Because there's so many letters, but it's doing the same thing we just did with 3 equations and 3 variables. So I just wanted to get across that if you write this out, it does actually work in general, and so that there isn't a precise proof. It's basically just logic. Okay, and that's why. And the second theorem says the success of Gauss's method. What you do is for that is you go up and you look at this linear system and say, well, in this first column, let's say one of these is not 0, right? Then I could swap it into the first place, then use a row combination operation to get rid of any of the other coefficients down below. Then you could say, look, then I don't have to, I can think about the smaller system, which is really just 2 equations and 2 variables. And I can say, well, one of these could be non-zero. If one of these is non-zero, swap it into the first place and and then use row combination operation to clear it off below. And you can see that you can just keep doing this. Okay, now, this idea of keep doing it is a little bit mysterious, and it leads to the idea of induction, which in this context, because you've got all these letters and names, is hard to sort of deal with, because it's so it's like you've just got so many symbols, it's hard to sort of learn to look at it and have it mean something. But that's the idea of those 2 theorems, and unfortunately they're the first 2 theorems you see in the course, because they're hard to read, not because they're complicated, but because they've got so many letters, it just like overloads your senses, so to speak. Okay.